Hi everyone. In this pretty short video, what I would like to do is take the familiar mean value theorem from single variable analysis and extend it as much as we can to functions of multiple variables. Now, what do I mean by as much as we can? It turns out if you want to take the mean value theorem and take it from a single variable setting to a multivariable setting, you need to insist that the function f that you are working with is scalar valued. So what I'm going to do now is take this statement and prove it. So if you read through this carefully, you'll notice it looks kind of like the regular mean value theorem. And then after we're done proving it, I will give you a demonstration, just a kind of counterexample, to show you why the function f cannot be vector valued. So this theorem is all about scalar valued functions of multiple variables. Now, this statement I felt was worth proving on its own. But this is really one special case of Taylor's theorem, which we are going to cover basically next in this lecture series. So you could kind of skip proving this as a standalone statement and just prove Taylor's theorem. However, I think it's worth it to go through this special case, A, because we see this case a lot. The mean value theorem is something that we talk about all the time. And B, I think if you understand this proof, it puts you in a really good place to think about extending it to not just this kind of expression, but basically we're going to build up this expression with Taylor's theorem. All right, so what does this say? Imagine that we have a scalar value function of multiple variables, which is differentiable. And it's possible it's defined on all of Rn, but if it isn't, imagine it has some open domain A, which I'm going to sketch. This is open, but I'm just going to sketch it with closed lines like that. Now, if you take any 2 points in A so that you can connect them with a straight line segment which stays in A. I didn't really give you a great way to break that in this picture. Imagine I go like that. There we go. Okay, so I could connect, say, this point to this point. We'll call this the point P and this the point X with a straight line segment. And XP and the straight line segment all live inside of the domain A. Okay, with my little adjustment here, which I might have made kind of blurry, you wouldn't want to use this theorem if I was trying to connect a point here to a point here. That just wouldn't be good because the straight line segment connecting those 2 points passes outside of the domain. Okay, so if this is the configuration that you're looking at, then somewhere between X and P, there's a point C, which I will add to this picture as, say, here, where we can say that the value of our function at X equals the value of our function at P plus the Jacobian at C times the difference vector X minus P. Okay, what I would like for you to do is take a moment to pause, and I'm going to give you 2 assignments. One is to rearrange this, or basically like rewrite it for a scalar value function of one variable, go back to the regular real analysis 1 version of the mean value theorem and see why this is an extension of that. So basically try to get from this to the one variable, single variable mean value theorem. So that's assignment number 1 in the break. Assignment number 2 is we are going to need to think about the straight line segment connecting X to P. So I drew the straight line. We have to work with that. So also take a moment to see if you can write down a parametrization. So parametrize the path that takes us from X to P. The best way to do this, I think, would have a time domain, a parameter domain from 0 to 1. That's a little bit of a hint. But just kind of revisit this idea of parametrizing a straight line segment. And I'm just going to give you a few seconds to pause and work through those 2 ideas. When we come back, I will answer both of those. So we'll relate this to the regular mean value theorem, and then I will give you the parametrized path. All right, let's see how you did. For the first exercise, I wanted you to relate this expression to the regular mean value theorem from single variable calculus. So let me say if n equals 1, meaning that the domain is from R, so it's one-dimensional domain, then what we can do is subtract over f of p. Well, actually, we could always do that. So this is always valid, but what isn't valid when your domain is in, say, R2 or higher is dividing by the expression x minus p. So if you're working on the real number line, x minus p is a scalar. X and p are different, so it's non-zero. And you can write this quotient. But if your inputs are vectors, do not write this. So please never divide by a vector. Okay, so so I just rearranged, I brought the x minus p over because that's something we're allowed to do when our domain is one-dimensional. And then on the right-hand side, we have df at c, but that's kind of funny notation to use when you're looking at a single variable function. So I would call that f prime of c. And then this is our familiar mean value theorem. So if I have some function like this and say this is the point, how about x, f of x, and this is the point p, f of p. On the left-hand side, we have the slope of the straight line connecting those 2 points. We call that a secant line. So this is the slope of the secant line on the left-hand side. And then the mean value theorem tells us that somewhere between x and p is a point c, where the derivative of f at c is the same value. That's like saying there's a tangent slope between these 2 points, which is equal to the secant slope. In this picture, there are 3 such locations. So here, here, and I didn't quite get it right, but it's somewhere in there. So that's one thing to recognize, is that this mean value theorem, whether we're working in the case n equals 1 or n greater than 1, which is what we're going to focus on for the rest of this video, it doesn't tell you where c is located except that it's between x and p. So somewhere on this line segment, there will be a point c that we will identify, but I don't know if it's here, here, here. Same thing here. I don't know, without drawing the function and knowing more about it, where c is located, nor do I know that c is unique. So there were 3 places on this graph where the tangent slope was parallel to the secant slope. Likewise, there could be 3 vector inputs from the straight line segment where this statement would be satisfied. Okay, so that was exercise number 1. Exercise number 2 was to parametrize the straight line segment. Whenever you're trying to parametrize a line, there's a quick way to do it if you have 2 points on the line. So I'm going to say r of t, this is my notation for this parametrized curve, or in this particular situation, is a parametrized straight line. If you know 2 points and you're trying to travel from one to the other, you can do 1 minus the parameter t times where you started. Let's start at p. Plus t times x. So let me make this a little better. Okay, sorry, that's supposed to be 1 minus t, and then t. Okay, this is a straight line, and notice if t equals 0, I wipe out this. This becomes 1. So at t equals 0, r of 0 is p. When t equals 1, if I plug 1 in for t, I get r of 1 is, this goes away, 1x, that's x. So we are traveling in this direction. P is now r of 0, x is r of 1. And then let me erase this. If you don't see immediately why this is a straight line segment, if we compute its tangent vectors, oops, sorry, r prime of t, it's a constant. So it's going to be x minus p, which should sound familiar given the statement that we're trying to prove. Okay, so we have constant tangent vectors. This is a straight line segment. When t equals 0, we are at p. When t equals 1, we're at x. If you wanted to give kind of like an open domain, you could say, let t go from just a little bit to the left of 0 to a little bit more than 1, but we're not going to worry about that. I'm just going to imagine us as interested in this curve from t equals 0 to t equals 1. Let me take a moment to erase this, and then we will prove this statement. I'm going to write it pretty efficiently, meaning I'm not going to introduce in r of t. It's right here. So I will write kind of a 1 or 2 line proof, given that we've already parametrized this line segment. Okay, let's do the proof. This is going to be a little bit more abbreviated than what I would write on paper. And also, as we do this proof, I assume that you've already worked through the proof of the regular scalar mean value theorem that we just talked about for n equals 1. Because of that theorem, you prove on its own in first semester analysis with things like Rolle's theorem. It doesn't need this configuration. So we're building off of that result. Okay, proof. Here's the thing. If you're trying to figure out what to do, I mean, I already gave you a big hint here by parametrizing the line segment. We are looking for a behavior on this line segment. So perhaps for f, we just really want to ask ourselves, how does f behave on the line segment? That is an act of composition. So let's compose f with r, just evaluate f along r. And just for notational purposes, let's call that composition H. Take a moment to look at this function. What is its domain? What is its codomain? What kind of function is this? What tools do we already have for this function? I hope you realize that h takes in the parameter t, that's scalars, sends us to the line segment, but then we plug that into f, which is scalar valued. Then h as a map goes from, let's say, 0 to 1. Again, you could extend that domain a little bit if you wanted to, but 0, 1, 2, a to f of a, which is a subset of r. So as a function in its own right, h is a scalar valued function of one variable. It's also differentiable because f is differentiable, r is smooth. This is a straight line. We've already computed its velocity vector. So h is the composition of differentiable functions. It's what you could think of as like a regular single variable calculus function. So we can just do h prime, and we can use any results that we have from real analysis 1 on h. So in particular, we can use the, let me call it n equals 1 MVT, the regular single variable MVT. Okay, I think I will mention that h is differentiable first. Then h is differentiable, and by the n equals 1 MVT, there is a value between 0 and 1. Be careful, I don't want to call this c, because I run the risk of confusing that with this vector between the vector x and the vector p. That's not where we're looking. We're looking at this time interval. So let me call it tau. Okay, so there's a point tau between these two values, 0 and 1. So there exists tau in the open interval from 0 to 1, so that instead of writing the secant equals tangent version of the n equals 1 mean value theorem that we had a moment ago, let me just put it directly into this. We know that this is valid for n equals 1 as it's written, except here I'm working with the function h, not the function f. So in this form, we would say h of 1 equals h of 0 plus h prime at tau 1 minus 0. We have it. We just have to translate from this back to f, really. So take a moment to, if you don't believe this version, of course, this is the regular mean value theorem. So we have h of 1 minus h of 0 divided by 1 minus 0. That's our secant slope. Here's the tangent slope that sits between them. Take a moment to translate this statement into a statement about f. See if you can get all the way to the final result. All right, I'm not going to finish the proof with full sentences. I'm just going to translate like this. I'll leave you to write out a nice ending for this. What is h of 1? H of 1 is f of r of 1. That's f of x. Likewise, h of 0 is f of p. 1 minus 0 is 1. We can basically ignore that difference there. This is just the number 1. H prime of t by the chain rule is going to be df at r of tau times r prime at tau. Okay. The thing is, what is r of tau? Well, we don't even know what tau is. We just know it's a number between 0 and 1. So whatever tau is, r of that lands us between 0 and 1, and that's what we want to think of as the vector c here, this input c. So this r of tau, let me put down here. We'll just keep diagramming out the sentence. This is c. So df at r of tau is df at c. And then r prime at tau, don't overthink that. R prime is constant. This is x minus p. Okay, again, I didn't write out a nice ending, but you can do that with 1 or 2 sentences now. So we have f of x equals f of p plus the Jacobian matrix at c times the velocity vector r prime, which is actually the vector x minus p. Let me just make one quick remark before we move on to the counterexample. if you try to extend this further to functions which are vector valued, f is scalar valued. So this Jacobian matrix, if you wanted to, you could write this as the gradient of f at c dotted with the vector x minus p. That's equivalent. Let me just make a little note of that. Usually that's actually my preference. I think when I wrote this out, I went with the Jacobian form just because we're going to build into Taylor's where you have like possibly multiple levels of differentiation happening here. But at this point, we have the result. So I think this is a really fun proof. We've talked about composing scalar valued functions on curves before. So here, like it came into the practice for us and we were able to make a proof with it. Again, this is a generalization of the mean value theorem that you would have already seen in real analysis 1. And then we are going to generalize it very soon with Taylor's theorem. I think this is a nice warm-up for Taylor's theorem. Okay, said enough about this proof. We will come back in just a moment, and I will give you a quick counterexample to the statement that this equality would work if f was vector valued. It won't work, and I'll give you just an example why not. Let's wrap up this video by discussing why this mean value theorem does not work if you look at a vector valued function. Say f is a function from Rn to Rm. If that's the case, then the equation that we have here, this would be the statement. It's a fundamentally different type of equality than what we just looked at. And the reason why is that the mean value theorem that we just proved for scalar valued functions has a scalar equal to another scalar. If I tried to say that the function f was vector valued, then this is not a scalar equals a scalar. It's a family of m equations. So it's like a system of m equations, and that very easily does not have a solution. So it's like you would need this equality for m different coordinates, and you might not have enough control. For each coordinate, you might be able to find some kind of interior point where a version of this is satisfied for the component function that you're looking at, but can you glue them all together? And the answer is no. Okay, so here is a counterexample. I tried to make this a very clean counterexample, and what I mean by that is while I've defined f as having a domain that looks like Rn, if you look at the outputs, it actually only depends on the first coordinate. So you could think of this as a function from R to R2. So it's like the smallest way to take a function and make it vector value. So from R to R2, or if you want to be kind of broad in language from Rn to R2, it works as that too. Let me have you work through the details here. So I am going to give you the A and B. If you don't want me to spoil it, you can go ahead and pause right now to try to come up with how this is a counterexample on your own. But if you'd like a little bit of a hint, here it is. There are more than one ways to proceed, but here's a way that works. So let A be the first standard basis vector. So that's 1 in the first coordinate and 0 is elsewhere. And let B be negative E1 or negative A. Okay, if you'd like to, you can go ahead and see if you can get to what will be a system of two equations and verify that those two equations do not have a solution. So it's an empty set solution, which means that this statement is not true for this function with these choices of A and B. Okay, let's compute the left-hand side. So what is f of b minus f of a? Oops, f of b minus f of a. That is going to be in vector form negative 1 squared sine of negative pi minus 1 squared sine of pi. I'm going to try to make this clean. So this is just 0 and 0. Okay. For the right-hand side, let's compute the Jacobian matrix in general. And actually, we can go ahead and say the Jacobian matrix at some point C, where the coordinates are C1 through Cn. F is a map here. The way I've presented it as a map from Rn to R2, that tells us that our Jacobian will be 2 by n. So we'll have 2 rows and n columns. The first row is to take x1 squared and differentiate that with respect to each of the n coordinates, but most of that's going to be 0. So we have 2x1, 0, 0, because that first coordinate has no dependence on x2 through xn. Likewise, for the second coordinate, derivative of cosine of pi x1, when we're looking at x1, the pi will pop out, that switch to cosine. Maybe I should just write it down. There we go. Okay. So that is the first coordinate on the second row. But similarly, that output there has no dependence on x2 through xn. So we have zeros. This matrix is 2 by n. Okay. If I take that and multiply it by b minus a, then that's going to be like multiplying it by the vector 2e1. Maybe I'll pause here if you didn't get this far and take a moment and see if you can now compute the right-hand side and, again, compare the left-hand side to the right-hand side. Okay, so the right-hand side, let me just do it here. We need df at c. Oh, sorry, I'm just realizing that I called this x1, but I was imagining that we are evaluating this at c. Little change here, I'm just going to make this c1. There we go. My apologies. Okay. Doesn't seem like a big change, but the idea is that we're trying to find some point C between A and B. So if we had such a point, this would be the associated matrix. Okay. So what is the right-hand side? It's going to be df at C times B minus A. But again, B minus A is like negative 2e1. And then if you take any matrix and multiply it by the first standard basis vector, it extracts the first column. That's here. We're going to multiply that by negative 2. So it's pretty quick multiplication once you realize, hey, E1 pulls out the first column. So this is going to be negative 4C1 and negative 2 pi cosine pi C1. Is that right? Yeah. We have a system of two equations for two unknowns. So that's really the message here, is that we have a system of equations, we might not be able to solve it. We need 0 to be equal to negative 4C1, but that tells us C1 is 0. Let me write that here. But then 0 also equals negative 2 pi cosine pi C1. But if you plug 0 in for C1, which it must be for the first line to be satisfied, we would have negative 2 pi times cosine of 0 is negative 2 pi, not 0. Okay, so this system of two equations did not have solution. Okay, that's really all we need to do to verify that something is not true, is find a counterexample. Here's a counterexample. So there is no mean value theorem for vector valued functions. Thank you for your attention.